Okay, so the next Laplace transform that I'm going to try and derive now would be the sine and cosine functions. So the Laplace transform of sine a of t will be the, as we said before, it's defined as a semi-infinite integral between infinity and 0 of f of t, which in this case is sine of at, e to the minus st dt, as we've said before. Now, how do we solve this integrand? Well, we could use integration by parts, or we could do something which will be a little bit more clever. What we could do is use complex integration to make this a lot simpler by maybe doing the following. So if we said, say, e to the j theta equals cosine theta plus j sine theta, what we can say is that, what can we say? Well, that's real, that's imaginary. Well, we can say that e to the j at equals cosine at plus j sine at. Okay, now how does that help you out, Adrian? Remember, we want to get sine at. I know, what we can do, we can say the following. Therefore, we can say that the imaginary part of e to the j at equals sine at. Bingo! Now the rest should be easy. Because what we can do is that we can make the substitution. Thank you, Euler. So now we can now say that the Laplace transform of sine at is simply going to be the semi-infinite integral of sine at. Well, we know that sine at is just the imaginary part of e to the j at. Yeah? Times by e to the minus st dt. So we can then simplify this to say that this is going to be just the imaginary part of this integral, semi-infinite integral, defined from positive infinity and 0, of e to the j at, e to the minus st dt. So let's simplify this. So that's going to be e to the j at minus st dt. Okay, let's keep going. This is looking good. Equals the imaginary component of the positive infinity and 0 of e to the commonality here is the t, e to the t, ja minus s dt. So now let's evaluate this integral, which should be quite easy to do. It's just going to be the imaginary part of 1 over ja minus s, e to the t, ja minus s. Yeah? Oh, sorry, I'm going mad. Evaluated at infinity and 0. Yeah. So let's simplify this further. So we can say that this is going to be the imaginary part of 1 over ja minus s. When t is infinity, remember, we said that s has to be sufficiently large such that the product of those two functions is going to tend to 0 when t tends to infinity. Yeah? Which means that the magnitude of s has to be greater than the magnitude of ja. And if that's true, then as t tends to infinity, this whole thing over here is going to tend to 0. Okay? So we can say that's going to be 0 evaluated at infinity minus e to the naught, which is 1. Okay? So now let's take this all the way back up, and we can say this is going to equal the imaginary part of, remember we're multiplying this by minus 1 now, 1 over s minus ja. By the way, another way to think of this would be to evaluate e to the minus t, s minus ja. And as t tends to infinity, we can see that's going to tend to 0. When t is 0, this thing is going to be 1. So that's just another way of thinking about this evaluation. Right, anyway, we're back over here. So we've got the imaginary part of 1 over s minus ja. Is that looking good? Well, it might look a bit confusing, but this is actually very, very good, because what we can do is that we can just multiply this by the complex conjugate. And this is going to make it really nice, hopefully. S plus JA over S plus JA. So that's going to equal the imaginary part of S plus JA on S squared minus A squared. That's going to be positive because of the J's. So now we have this. Now this looks a little bit scary, but it's not, because we can now say that this is going to be the imaginary part of S on S squared plus A squared. I'm just taking this component down, plus J, the imaginary part, A on S squared plus A squared. And this is beautiful, because now we have the imaginary part of this whole thing. Well, the imaginary part of this whole thing, of S on S squared plus J, A on S squared plus A squared, is just going to be the imaginary part, A on S squared plus A squared. QED. And that's it. So we can say that the Laplace transform of sine AT is just going to be A on S squared plus A squared. Simple as that. And if you notice, we can actually find very easily what the Laplace transform of cosine AT is going to be as well, because we would set this up in exactly the same way, except when we get down to Euler over here, we can say that the real part of e to the JAT is going to be cosine AT, not the imaginary part. But the integration is going to be exactly the same, because if we replace here the real part, e to the JAT equals cosine AT, then this is just going to be real e to the JAT, e to the minus st dt, evaluated at the semi-infinite integral, positive infinity and 0. And that's going to be for the cosine AT. So if we would basically get all the way down to here again, except this would be the real part of S of this whole function. So we can easily say from here by observation that the Laplace transform of cosine AT is going to simply be S on S squared plus A squared. Nice and simple.